good morning, and welcome back to microprocessor course. In today's class, we are going to have a quick look through about the cache memory, then we learn serial access memory, then content addressable memory, then we're gonna talk about cache memory write policy. So before we start today's class, please scan the QR code for your attendance. Please avoid making some typos, and always use the same email ID, the PDX email ID. Is your VPN on? Switch off VPN. Huh? Mine is working.
Teacher, my iPhone system is updating, so I can't scan.
Everybody has done with this? Oh, fine. Talk to me during break time. Everybody has done with this? You can't? Okay. How many can't scan this and enter the information correctly? How many? Only two? Great. All right, so we're gonna have a short review about the cache memory. The cache memory is very important in our computer system because it does store the most recently used data to avoid multiple accesses of the central processing unit to the main memory. So it's there to balance the high-speed memory and expensive memory with the large memory system and less expensive memory. So it is very important to know that the cache memory is between the central processing unit and the main memory. And as we have seen, we have different levels of the cache memory depending on the technology. So it is very important to note that because the cache memory is smaller than the main memory, we need some caching mapping techniques which can allow us to system to write some main blocks from the main memory to the cache line. So we learned about those cache mapping techniques, starting with the direct mapped. These techniques allow a block from the main memory to be allocated into a specific cache line. The cache line, to found the cache line for a main block memory, we do the block number. This is the block from the main memory, mod the number of cache line. Number of cache lines. If you have a block 12 from the main memory and we have 8 cache line, So to found the cache line first cache mapping technique. The second one is fully associative. For this fully associative cache mapping technique, a block from the main memory can be loaded into any cache line. Block from main memory can be loaded into any cache line. Any cache location. So the third one is set way associative. This stands between the previous one, between the direct mapped and the fully associative. To found a set for a block from the main memory, we do the block number, modulation, the number of sets, So if we have our block example, if we have block 12 from the main memory, and we have 4 set way associative, 4 sets. To find the block, the set for the block number 12, we do a block number that is 12 more than the total number of sets. So that means our block 12 from the main memory will be loaded into the cache line 0. So there are some other types of serial memory. We needed to learn these following types of memory, including the serial access memory and the content addressable memory. This is going to help us a bit to understand how does the fully associative cache memory organization does handle the hits. So what is a serial access memory? A serial access memory, as is depicted by this picture on the screen, is commonly used in digital system to manage data in a first in, first out queue order. So it is typically consists of set of registers where data is written and read in a specific order. So it has to be, for example, a sequential read order. Now here we have the picture on the screen, which does depict a queue. We have a queue. Let's imagine this is the FIFO queue, and then we have the right click here. This is the signal for writing data into the key, and this is the read signal to read the data from the queue. So it has to be in a specific order. So this is a signal to indicate that this queue is full, and this is the signal to indicate that the queue is empty. There is nothing in the queue. So now you do understand that the serial memory is a type of memory that is being used in digital system to manage data in a first in, first out queue. The next one is content addressable memory, CAM. This type of memory is a bit different from the ones that we have learned before, including the random access memory. The normal memory normally returns data based on the address. That means we have address points that they need to point to a specific location of the data. For content addressable memory, now we just learned about serial access memory. For the content addressable memory, the system does store the data with two important factors, the addressable memory. So a content addressable memory is a type of memory where data is accessed based on content laid down address. If you still remember from the previous memory, including the random access memory, the search of the data is done via the addresses. But for the content addressable memory, the data is accessed via content rather than an address. In other words, we need to understand that the content addressable memory allows for parallel searching of its content. It is often called associative memory. Now, here we have the content addressable memory picture. We have the lead signal and we have the write signal as well. So the system needed to check if there is a match. If there is a match, they have to return the address of the data, and if there is no match, that means that it is a miss. So for normal memory, that is, for example, for random access memory, the system asks for data by location. For LAM, the system asks data by location. For a CAM, content addressable memory, the system does not look for the data via the address. Instead, the system asks for address by data. The system asks address by content, by data. So for random access memory, the system asks for data by location, address memory. What do you have at this address memory? So the system does provide address location, and the data will be returned to the system based on a specific memory location. So for example, it does say, okay, give me the entry at the memory location 5. For the content addressable memory, the system asks for address by content. That means here is a value, here is a key. I want the system return the address of the value. So that is the main difference between the content addressable memory and the CAM. Now we have virtual memory translation, look-aside buffer. We needed to understand that the virtual address is sent here to the CAM, and here we have the virtual address. This virtual address is sent to the CAM, which we check for a matching virtual page number. If there is a matching, that means it is a hit. The corresponding physical page number will be fetched from the static log. So there is a virtual address from the system. Then if there is a matching into the content addressable memory, this is what we call a hit. And then the physical address, which corresponds to the virtual address, will be fetched from the static LAM to produce the physical address. Now, if there is a miss, the translation has to be obtained from the page table, which will take much longer. So this picture on the screen depicts the translation of the virtual address to the physical address. When the virtual address is not, there is no match of the virtual address into the static LAM. So we have a hit if the corresponding page number is in the static LAM. If it's not there, it has to be fetched from the page table, which will take much longer. Now, we have a memory CAM. Here we have addresses which are linked with side of the diagram shows the attempt to find the address of a specific data variable. Now, for example, here we have a variable which is stored at this memory location. The decoder needed to find out what is the address of this variable 37, or what is the address for the variable 01. What is the address value for 00? So the decoder then is to find a specific address to a specific data, because it's the content address of memory. We need to find an address for a specific data, which is the opposite for the normal memory system that we have learned. For the other memory system that we have learned, we have address memories which are linked to a specific data. Then the system needed to return the data based on the memory address. If you still remember, for random access memory, for example, these are memory addresses. Let's say this is OX00, OX01, and OXFF. So at each memory location we have varies. We have different values at each memory location. Now the system for a random access memory, the system will return this data based on the memory address. The system will ask for the data based on a memory address. But for the content addressable memory, the system will return a specific memory address based on the content of the data. That is the main difference. For example, the system will say, okay, I want you, do you have, which value do you have at this memory location? This is for the random access memory. So for COM, the system asks for address via data. For random access memory, the system asks for data based on memory address. Clear? So for random access memory, the system will ask, return the value which is linked with this memory address. For the content addressable memory, the system will ask what is the address of this data. So the system sets the address via the data. Now we needed to talk about some cache performance metrics. If you still remember, we talked about this terminology. We have a hit when we have the desired item, and the item is available in the upper level memory, let's say in the cache in our case. Now we have the miss if the data is not available in the cache. So the request needed to be done, needed to be expanded to the next level of the memory. Now we have a hit. These are the terminology that you are almost familiar with. Hit. That is, we have the data in the cache. Data is in the cache. That is hit. Is in cache. Miss. Data is not in cache. So the fetch needs to be expanded to the next level of the memory. So we have the hit rate. That is the probability a data, an item is in the time, which is equals to the heat rate. What is the probability of having an item into the cache memory, times the height time, how long does it take to return the item to the system when it is in the cache, plus the miss rate. The miss rate, if the data is not in the cache, this is the probability of not having an item in the cache, that is the miss penalty, times the miss time. How long does it take the system to return the data if the data is not in the cache? So we have the average memory access time, which is equals to the heat rate times the heat time plus the miss rate times the miss time. So we have a simple example here. A cache which has a heat rate HR that is 0.9. We have 0.9 as heat rate, and the heat time is 5 nanoseconds. 5 nanoseconds. Then we need the miss rate. What is the miss rate here? The miss rate, which is equals to 1 minus the heat rate. So the miss rate is 515. 515. What is the miss rate? Absent. 615. 615. 515. Huh? Absent. So the miss rate is equals to 1 minus 0.9, that is 0.1. Then we have the miss time, which is 100 nanoseconds. Then we can easily find the average memory access time. Here we have 4.5 nanoseconds plus 10 nanoseconds. Then we have 14.5 nanoseconds. So this is a simple example on finding the average memory access time. Now, we need to have a short review on cache memory logic organization before we start the cache write policy. Now, we have the cache memory, which is smaller than the main memory. That means that not all the blocks from the main memory can be loaded into the cache memory at the same time. So we have fewer cache line than main memory blocks. So we need some cache mapping techniques. A method which is used to determine which main memory block can occupy which cache line. So we have the mapping techniques which decide the cache line organization. We have talked about the 3 different cache mapping, including the direct one, associative, and the set associative. So a short review for the direct mapping, we have it is a simple one, and each memory block mapped to only one possible line. The mapping is using the following expression: I equals to J modulo M for direct map. We talked about it. We have the total number of cache lines, and we have the block number. So the cache line is equal to the block number modulo the total number of the cache line. Then we can find a specific cache line for a specific memory main memory block. So this is still easiest one, the easiest cache mapping technique. Now we have a simple picture to depict the direct mapping. We have these are the blocks from the main memory, and these are the fast M blocks from the main memory. We have many blocks in the cache memory. That means these are only the fast M specific block from the main memory. Now, we have address from the CPU. Address from the CPU. This is for the direct mapping cache organization. We have the tag here. Then we have index. Then we have the offset. The offset here is how many bits? Is W bit. And we have R bit for index, and we have S minus R for the tag. So what does this mean? The mapping function is easily implemented for direct mapped caching technique. So this figure on the screen depicts the general mechanism. For the purpose of the cache access, each main memory block needed to map to a specific cache line. Now we have the tag here which verify if the data is correct or not. Then we have the index, which is decide the line in which the cache, the main block memory will be loaded in, and we have the offset, which is decide the word within a byte. Now we have W least significant bit. This is the least significant bit, which needed to select a word or a byte within a block. Now, if you still remember, we have the cache memory. So these are the line 0, 1, 2, let's say L minus 1. And here we have the tag. And here we have the block. Okay? Now, here, this is the address from the central processing unit. This is the address from the central processing unit. So the least significant bit here, this is W bit. They are there to select a word or a byte within a word. Now here, inside this block, we may have word or byte, depending on how large is the data. Now, this is W bit. They are there to select a specific word or a byte within a block. Now, the S remaining bit here, the S remaining bit is to select 2 to the power of n main memory block. So we have here the cache implementation. For the cache implementation, we have S minus R, the most significant bits that are there to indicate the task. Then the R, this technique. The next one is fully associative. For fully associative, we know that there is no requirement for each block from the main memory to be loaded into a specific cache line. That means that we have a block from the main memory which can be loaded into any cache location. So we have only address which does not fit into tag and not index. We have only the tag, and we don't have lines. We don't know which line does the block from the main memory will be loaded into which cache line. So we do have tag only, not index. But for the direct mapped caching technique, we have tag and we have also index. We have also line number because each block from the main memory needed to be loaded into a specific cache line. So that's why we need the index. So here, any address to any location into cache. This is what it means for the fully associative. Now, we have here the tag. As you can see, it is easily depicted by the feature here that we don't have the index, we don't have the line number. We only have the least significant bit, which is there to indicate the offset. That means to determine which byte or when within the block. And we have the tag, which is S bit, and you see we have the comma now. We have the comma here. This tag is the comma. Instead of a simple comma in the cache memory, we have a comma. As you have seen for comma, the system needed to retrieve an address based on the data, not return the data based on address. Now, you see, this is more complicated. To determine whether a block is in the cache control must do a check, must have to assess every line is tagged for a match, and it has to be done at the same time. Since the system does not know in which line does the cache memory hold the data, it has to do the search in the whole line at one time. That's why we have many comparators. So if we have found the data into the cache memory, that is a hit. If it is not there, that is a miss. So if it is a hit, a line that contain the data will be returned to the central processing unit. That means a location that contains the data will be returned to the central processing unit because we are using the count. And here we have the block. The block can be found in the static map. So we have here many comparators for the fully associative, which can help the system to determine whether a block of the data is available in the cache or not. Now, if we have address length of S plus W, that is the tag. This is for direct mapped. This is for direct mapped. And for fully associative, we don't need the address bit fed into the index. We only have the tag. We only have tag and the offsets. We only have tag and the offsets. This is for fully associative. Now, if we have the address length which is depicted by this feature, we have tag bit plus the offset bit, that is S plus W bit, because we have the bit for the tag is S and the bit for the offset is W. So that means we have address length which is S plus W. Now number of bits here for the offset determine the width or the bytes within the block. So we can easily calculate the block size. Block size, which is also called the line size, which is equals to the power of the number of bits in the offset. That is W. Now we can also calculate the number of blocks in the main memory. That is 2 to the power of S. 2 to the power of S, which is the total number of bits in the tag. So we have number of blocks in the main memory, number of blocks in main memory, which is equals to the power of S, which is the total number of bits in tag. Now, the number of lines in the cache cannot be determined because here we don't have the number of bits for the index to determine the total number of bits into the cache line. That means it is very difficult to determine the total number of lines in the cache because we don't know the number of bits for the index. Whereas for the previous one, there is a probability to determine the number of bits. We can determine the number of bits for direct map because we know that the total number of bits for the line number, it is R. So we can easily find out the number of lines in the cache, which is 2 to the power of R. Since we have here R bits for the index, we can easily determine the total number of lines for direct map caching techniques. But for fully associative, it is quite difficult to find the total number of lines in the cache because we don't know the line numbers. We don't know the total number of bits which are set to the index. Now, for set associative, we know that we can find a specific set for a specific memory, main memory block. As we have seen here, for set weight associative, if we have the block number from the main memory, we can find a specific line for the block by doing the block number mod, the number of sets. So that means we can find a specific line for a specific block from the main memory. So we have the address, which is split into the tag, and the index as for the direct map techniques. And each set has multiple places for each index. Now you see, this is direct map. We have a number of lines, and for set weight associative, we have different sets, and in set we have different lines. So each set has multiple places for each index. So two-way set associative has 2 locations per index, and four-way set associative has 4 locations per index. So this is set associative. So this is your 5-minute break. Take your break. We're gonna resume class after break. Let me check. Is your VPN on? It's weird because normally you should not switch on your VPN.